Alright, so we're going to talk about divisibility rules now. And what I mean by that is the following. Let's look at this example. Is 2 a factor of whatever this number is? What is this? 1, 2, 3, 4, 5, 6, 7, 8. 64,790,471. Now, I don't think anybody here that's watching this video is doing some long division to check this. What they are doing is they notice, hey, look, the last digit is not divisible by 2, so the whole number isn't divisible by 2. So we can say no, since 2 isn't a factor of that last digit. The last digit is odd, it's not even. So we know, without doing any long division, that 2 isn't a factor of this number. So that's kind of easy, but there are divisibility rules for lots of other numbers as well. In fact, we're going to do rules for, well, we're going to do 2, 3, 4, 5, 6. We're not going to do 7 because it's a little complicated. We might mention it later, but we're not going to prove it. 10 and 11. So we'll put 7 in here with like a frowny face because it's a little more complicated, but that's okay. We can still do all of these other ones. Not only are we going to do them, we're going to explain why these divisibility rules work. And it all comes down to place value. That's kind of the key with this, is these divisibility rules use what's inherent in place value to help us out. And we're going to prove these using the theorems that we did in the last video, theorems 1, 2, and 3. Now, I want to make a note. In fact, 2 notes. The first note is that we will only deal with 4-digit numbers just for convenience, so we don't run into some notation problems. But the idea works for any number of digits. So that's the first note I want to make. We're going to limit ourselves to 4-digit numbers. The second thing is that if I write something like this, A, B, C, D, and I put a bracket under it, what that means, that's not A times B times C times D. I'm going to define this notation of putting a bracket under something like that, meaning this is a 4-digit number here. So this is the same as A times 1,000 plus B times 100 plus C times 10 plus D, where A, B, C, and D are whatever digits in base 10. So I'm thinking of this as a 4-digit number, not A times B times C times D. So that's going to be important to us. And just as a little other refresher, I just mean the expanded form here. We had a name for this. We're just writing this 4-digit number in its expanded form. So this is like if the number was 7562, that's 7 times 1,000, or 7,000 plus 5 times 100, or 500 plus 6 times 10, or 60 plus 2. So that's what I'm thinking of when I write this notation here. So here we have this 4-digit number, A, B, C, D, written in its expanded form. Now, the key thing to note for this, if we're looking for the divisibility rule for 2, let's try and find as many things that are divisible by 2 that we can. Hey, look at this. 1,000's definitely divisible by 2. 500 times 2 is 1,000. 100's divisible by 2. 10's divisible by 2. D, well, D can be any digit we like, so that we have to check. But we know for sure that 1,000 has a factor of 2, so does 100, so does 10. And by Theorem 1, we know that A times 1,000 does as well. That's a multiple of 1,000. Any multiple of 1,000 has a factor of 2 as well. Any multiple of 100 has a factor of 2. Any multiple of 10 has a factor of 2. So let's write this in here. So, well, let's mark this down. We know that this is divisible by Theorem 1. Since 2 is a factor of 1,000, any multiple, sorry, 2 is a factor of any multiple of 1,000. Since 2 is a factor of 100, 2 is a factor of any multiple of 100. And since 2 is a factor of 10, 2 is a factor of any multiple of 10. We can't say anything about D yet. In fact, that's okay. But look at this. We have the sum of 3 numbers here, and each of those numbers is divisible by 2. And Theorem 2 says, if you have 2 numbers that are divisible by 2, so is their sum. And I'm hiding a little bit of detail, but I think it's pretty easy to see. Well, it doesn't stop at 2 numbers, it's any number of numbers. If you have 3 numbers and they're all divisible by 2, then the sum of these 3 numbers is divisible by 2. You just apply that theorem twice. You apply it once for, say, these 2 numbers, then this sum is divisible by 2, and then you apply it to this sum and this number, and that's divisible by 2. So Theorem 2 gives us this. So we know by Theorem 2 that this entire sum here, A times 1,000 plus B times 100 plus C times 10, that is divisible by 2. But D, well, we don't know what D is. D we're just going to have to check. Okay, so that's the idea here. Let's write it up. So, let's write down what the rule is. If the last digit, in fact, we have a name for the last digit, it's D. So, let's say if 2 is a factor of D, then 2 is a factor of the 4-digit number A, B, C, D. So that is our rule. We just need to check that last digit. And it works the other way as well. If 2 isn't a factor of D, then 2 isn't a factor of A, B, C, D, that 4-digit number. And we can rewrite this if you want. This is a biconditional statement if you think about it. So it's true exactly when 2 is a factor of D and 2 is a factor of A, B, C, D. They are the same thing. So we can rewrite this if you like with the following sentence. 2 is a factor of D exactly when 2 is a factor of the entire number. So this covers all scenarios. Now let's go ahead and write up a proof for this. Okay, so let's go ahead and do it. So we have our 4-digit number A, B, C, D. So let's consider, or let's note that 2 is a factor of 10, 2 is a factor of 100, and 2 is a factor of 1,000. So by Theorem 1, if you don't remember what Theorem 1 says, go back and have a look at it, but the long and short of it is that if A is a factor of B, then A is a factor of any multiple of B. So by Theorem 1, we have that 2 is a factor of A times 1,000. That's a multiple of 1,000. 2 is a factor of B times 100. That's a multiple of 100. And 2 is a factor of C times 10. All right, so we know those things. And by Theorem 2, we have that 2 is a factor of the sum of these guys. So A times 1,000, B times 100, C times 10 are all divisible by 2, so their sum must be as well. So 2 is a factor of A times 1,000 plus B times 100 plus C times 10. Okay. Now, we get both bits of this theorem just from the two cases here. If 2 is a factor of D, if D is divisible by 2, then we can apply Theorem 2 again. We have this number, which is divisible by 2, and then this number is divisible by 2, so the whole thing is divisible by 2. So Theorem 2 applies. But if it's not, if this is an odd number, then Theorem 3 applies. This number is divisible by 2, but this number isn't. And remember, Theorem 3 says if you have the sum of something divisible by 2 and something that isn't, then the sum is not. Okay. So, now, if, or let's say assume, go wrong color here. Let me fix this. Let's go black. Assume 2 is a factor of D. Then, I should put a period here and a capital letter, since that is a new sentence. Then, by Theorem 2, we have that 2 is a factor of A times 1,000 plus B times 100 plus C times 10 plus D, which is indeed just the expanded form of this ABCD number. And in some sense, to see how Theorem 2 applies, the way I'm bracketing it is like this. There's my first number. I know that's divisible by 2. And that number is divisible by 2 because we're assuming we're in that case. Okay. And then let's do the other way. Assume 2 isn't a factor of D. Then now, by Theorem 3, we have 2 isn't a factor of A times 1,000 plus B times 100 plus C times 10 plus D. And again, I'm bracketing it in the same way. Here we have this bit is divisible by 2, but D isn't. So Theorem 3 says, well, if you have one number that is divisible by 2 and one number that's not, the sum is not divisible by 2. Okay, so there we go. We've shown it. In fact, we can put a little square here. There's the divisibility rule for 2. So now, with that same idea, using this as a guide, see if you can come up with the proof for the divisibility rule for 5. In fact, there's a few that you could do. In fact, I think it's a good idea now. Try to do the rules for 5 for sure, and then think about 4 and 8 as well. 5 is incredibly similar to 2. 4 and 8 are also similar, but you have to think about, well, which of these numbers is now definitely divisible by 4 or divisible by 8? Well, 10 isn't divisible by 4 anymore. 100 still is, and 1,000 still is. So maybe I have to check something different. So pause the video now and see if you can figure this out. Spend some time doing this. It's a really, really good exercise. Okay, now that we're back, let's talk about the divisibility rule for 5. Well, we know if a number is divisible by 5 or not. We know what's going on here. Let me just kind of write this in yellow, just in a little side thing, and talk about it. Well, the number 2300, we know that's divisible by 5, because when we look at the last digit is 0 or 5. And if we think about it, another way of saying that is the last digit is divisible by 5. And that's very, very similar to the divisibility rule for 2. So really, if you thought about it, all you had to do is everywhere that you see a 2 here in this proof, just change it to a 5. The exact same thing happens. In fact, the reason that is because 10 is made up of two prime factors, 2 and 5, and they're going to behave the same way. So let's do the rule for 5. In fact, I'm just going to pause the video. I'm going to erase all 2's, replace them with 5's. I think I'll do it in a different color, just so it's easy to see, maybe with red. And then just update it. You have a new rule now. All right, now that we're back, literally that's the only change we need to make. 10 is 5 times 2. So everything holds for divisibility for 2, that holds for 5, as long as you just replace a 2 with a 5. Everything still holds. 5's a factor of 10, 5's a factor of 100, 5's a factor of 1,000. So the proof and the idea is literally the exact same. We just need to look at each place value separately, and the only one that we know that's not guaranteed to be divisible by 5 is this last guy. Now, the astute among you probably noticed something that I didn't mention. There's another number that I can replace with 2, or I can replace 5 and 2 with, and this whole thing still works. Can you think of another number that's a factor of 10, 100, and 1,000? So pause the video and think about that. Alright, so hopefully the number that you came up with was 10. I guess 1 as well, but divisibility rule for 1. There's no divisibility rule for 1. 1 is divisible. 1's a factor of everything. But numbers that actually matter, 10. So we could replace all these 5's with a 10, and we get the exact same thing. So I'm going to pause the video now, and I'm just going to erase all the 5's, and I'm going to replace them by 10's. I guess I'll use green this time. Since I already used black, I used red. Maybe I'll use green. That's fine. So there we go. Again, we get the rule for 10 now as well. In fact, maybe I'll write that in. We get the rule for 10. So we've just done 2, 5, and 10. And in some sense, and in fact, in every sense, it's basically the exact same idea. If you break up the number in its expanded form in terms of place value, we know that the tens digit and everything to the left of it is divisible by 2, 5, or 10. So the only thing you need to check is that ones digit. So now let's go and have a look at the rules for 4 and 8. All right. So here's what we know so far. Let's talk about the divisibility rule for 4. We know for sure that, I'm just going to do some workspace over here. We know for sure that 4 is a factor of 100. 4 times 25 is 100. 4 is a factor of 1,000. 4 times 250 is 1,000. Okay, so we can apply that same idea from the divisibility rules for 2 and 5 to the divisibility rule for 4. Well, we know that these two numbers are definitely divisible by 4. So the ones where we don't know are these guys. So this is what we're going to have to check now. If the last 2 digits are divisible by 4. So that's the idea. The work is almost going to be the exact same, except instead of just the last digit, we have to check the last 2 digits. Okay, so we know the idea. Again, we know this is divisible by 4 by Theorem 2, since both of these guys are. Let's write it up. So the divisibility rule for 4. And I'll use that exactly when notation to say it covers every single case. So 4 is a factor of the 4-digit number A, B, C, D, exactly when, and I should put the bracket under there, 4 is a factor of the 2-digit number CD. So you need to check the last 2 digits. So we'll prove it, and then we'll do an example just to make sure we know how it works. Okay, so the proof's going to be the same as the first. Since 4 is a factor of 100 and 4 is a factor of 1,000, well, 4 is going to be a factor of any multiple of 100 and 1,000. So we know by Theorem 1, 4 is a factor of, we'll do it in the same order here, A times 1,000, and 4 is a factor of B times 100. Maybe it doesn't really matter, but I'll erase this just to keep it in the same order. I'll do 1,000, then 100. Okay, that's great. Now, by Theorem 2, four is a factor of the sum of these guys, A times 1,000 plus B times 100. Now, we need to do those 2 cases. We need to assume that 4 is a factor of the other 2-digit number at the end, CD. Then, by Theorem 2, we know 4 must be a factor of A times 1,000 plus B times 100 plus C times 10 plus D. And the way I'm bracketing it now is as follows. There's the number we know for sure in all cases is divisible by 4. And the C times 10 plus D, that's what we have to check. If it is, well, we know the entire number is divisible by 4 since Theorem 2 applies. And let's now assume that 4 isn't a factor of that 2-digit number CD. Then Theorem 3 tells us 4 isn't a factor of A times 1,000, A times 1,000 plus B times 100 plus C times 10 plus D. I'm bracketing it in the same way. I'm thinking of it as these 2 numbers. Now we have this number that is definitely divisible by 4. It has a factor of 4. But this number does not. We're in the case where it doesn't. So Theorem 3 says if you have one that does and one that isn't, you still have that remainder kicking around when you add these together. So it doesn't have a the sum doesn't have a factor of 4. So there's a rule. Let's check. Let's do an example and see how to use this. Maybe I'll scroll a little bit because I don't need that much space. So is 4 a factor of 2309464? Okay, so this rule says that all we need to do is check if 4 is a factor of the last 2 digits. So let's do it. Is 4 a factor of 64? We can do a little long division to check, or if you can see 4 times 16 is 64, you can just do that. But if you were to do long division to check, hey, look at this, remainder 0. 4 times 16 is 64. There's no remainder, so the answer is yes, since 4 is a factor of the last 2 digits. So that's how the rule for 4 works. All you needed to check was the last 2. All right, so I'm not going to prove the divisibility rule for 8. It's pretty much the exact same thing as 4 and 2 and 5, in fact. But the difference is, well, except the only one of these terms that's guaranteed to be divisible by 8 is this guy, because 8 is a factor of 1,000. 8 times 125 is 1,000. 8 isn't a factor of 100, so we don't know if this is a factor of, if 8 is a factor of this number. Same with 10, same with the ones digit. So this sum here is what we need to check, which is the last 3 digits, B, C, D, the number made up of those. And if you want to try to write up the proof, I think it's a good exercise. Just use the last 3 that we did as an example. And finally, well, let's just do an example to see how it works. Is 8 a factor of 9, 7, 2, 1, 1? Let's do 7, 8, 2. So our rule says all we need to do is check if the last 3 digits are divisible by 8. So let's go ahead and check them. Is 8 a factor of 782? If we get no remainder when we do long division, then we're good to go. 8 times 9 is 72. We subtract, we get 6. 8 goes into 62 7 times. We subtract. We have a remainder of 6. So hey, look at this. 8 is a factor. 8 isn't a factor of 782, so we know that it's not going to be a factor of this longer number that has the last 3 digits, 782. It doesn't matter what these numbers are here. I know we said we only did these for 4-digit numbers, but 8's going to be a factor of 10,000, 100,000, a million, 10 million, 100 million, whatever. It's just not a factor of 100, 10, and 1. So we still just need to check those last 3 digits. Let's talk about this important theorem here, and it's pretty easy once we write down what's going on. And we can see how it'll be useful right after we prove this. So this is basically saying if A is a factor of B and B is a factor of C, then A is a factor of C. And the reason that's kind of important, let me do an example first, is let's say we know 2 is a factor of 8. And if we know 8's a factor of, say, something along the lines of 4, 7, 2, 9, 8, 0, 0, if we know 8's a factor of that number, we know 2's a factor of 8 easily, then we don't need to do any work to say that 2's a factor of that number as well. 4, 7, 2, 9, 8, 0, 0. So we get all smaller factors too. So if we know a number is divisible by 8, it's also divisible by 4, and it's divisible by 2. So that's a really cool thing. Let's prove this. It's not particularly hard. So let's assume that A is a factor of B and B is a factor of C. What does this mean? This means that we can write B as A times some number and C as B times some other number. And let's say I introduced n1 and n2. They're just some whole numbers. We know B is a multiple of A. That's what this is saying. Same as saying A is a factor of B. B is a multiple of A. So A times something gives you B. C is a multiple of B. B times something gives you C for these somethings. We don't know what they are. Doesn't particularly matter. So we need to show that we can write C as A times something, and that something better be a whole number. So that's what's going on here. If we can show this, this means that A is a factor of C. We can write C as A times some number. Okay, now we have to be a little bit clever. We know what we're looking for. We just have to see how to get it. Well, here I have C equals something, so maybe using this equation would be a good start. Maybe I can do something with this right-hand side to make it look like A times some number. And if I think about it, I have this B here, and this B is A times some number. So I can substitute this equation in for here, and then I'm going to get A times n1 times n2. And n1 times n2 will be my whole number. So let's say, let's give names to these. Let's call this 1, and let's call this 2. All right, so substituting 1 into 2, we have that C equals, well, B is A times n1. B equals A times n1, so here's my B, so I can replace that by A times n1, and then I have it times n2. So this is B times n2, B times n2. And then let me just re-bracket this. So this is going to be A times n1 times n2. And hey, look at this. This is the product of two whole numbers, so that's another whole number. So since the whole numbers is closed under multiplication, we have that A is indeed a factor of C. I wrote C as A times some whole number, so I'm done. So that's going to be a very useful result going forward.